Since you're going to be doing a fair amount of vector problems, I think it's worth taking just a little bit of time to try and simplify some of the math so that you have some pre-made formulas for your formulas page as you're thinking through what you need to do to solve these problems. Let's go through and just do a couple of these pretty quick. Anytime you're doing vector addition, you're going to end up with some sort of a triangle. And it's going to have an x part and it's going to have a y part, and you're going to go ahead and find the r. And that triangle might be an x part this way and a y part that way with a resultant down here, but it doesn't really matter. It's all going to be broken down into x's and y's. So when you guys have been working with your formulas, you've been thinking opposites, adjacents, and all of those sorts of things. But since we're going to be breaking these things down into x parts and y parts, or x components and y components, then I think let's start talking about those in terms of x and y. So one thing you're going to do when you've got to find the x part of a vector is that you're going to use your cosine function because you're going to use the adjacent over the hypotenuse here. So you have this cosine theta equals the adjacent over the hypotenuse. And we can sort of reimagine that as the x over the r, or the x component over the either the resultant vector, or if it's an initial vector, we could just call it the main vector we're working with. So let's rearrange that. If cosine theta equals x over r, what I really want is the x component when I'm breaking these things down. So with a little bit of algebra magic, if you take that times r and this times r, you end up with x equals r times cosine theta. Or if you prefer, you could have x equals cosine theta times r. And with a little bit of thinking about it, you're going to have the same sort of setup for your y components when you have a vector and you're trying to break it down. So again, you would have sine theta equals your opposite over your hypotenuse. Again, subbing in x's and y's, we would have sine theta equals y over r. If we rearrange that, then again, we end up with this sort of set of formulas. We have x equals cosine theta times r, and we're going to have y equals sine of theta times r. And a lot of times when we're working to find the angle, we have this formula that tangent theta equals the opposite over the adjacent. We can rethink that as tangent theta is y over x, but we don't really need to find the tangent, we need to find the angle. So what we'll really have is the inverse tangent of y over x equals theta. So that's what I'm actually going to be doing. Theta equals the inverse tangent of y over x. And so now if we want to find the x component, we just take the cosine theta times r, or the hypotenuse. If we want the y component, we have the sine theta times r to find that vertical component. If we want to find the angle, we're going to be using the inverse tangent of y over x. And then sometimes we're going to be using the resultant formula for Pythagorean theorem. So I'm going to leave a little box in the middle there. If I've got a squared plus b squared equals c squared, well, side A, side B, side C, right? Which is really the x component of the vector plus the y component of the vector equals the resultant. But what I really want is r. And so to get r by itself, it's being squared, so I'm going to take the square root of it. But if I do it here, I do it here. So I end up with r equals the square root of x squared plus y squared I'll flip that back around. R equals the square root of x squared plus y squared. And then I don't have to go through this algebraic rigmarole every time I want to do it. I just have that the resultant vector equals the square root of x squared plus y squared. And this right here becomes my formula pack for taking vectors, breaking them down into components, and then re-adding them together. So make sure that you have these 4 versions of those formulas handy in your formula sheet when you go to do problems like this.